In the earliest days of computing, changing a machine's task required physical labor. Operators had to manually pull, reroute, and plug heavy braided wires into massive matrices just to run a new calculation. Every distinct program demanded a unique physical hardwiring of the system. The software logic was indistinguishable from the chaos of the hardware. Later systems attempted to streamline this process by feeding instructions mechanically. Operators used long spools of punched paper tape to sequence the machine's actions. The true leap forward occurred when engineers stopped relying on external, physical mechanisms. They began storing machine code, the actual program instructions, electronically or optically, directly inside the computer's own memory. By holding the instructions internally, a central processor could fetch and execute them serially, one after another, without a human operator ever touching a wire. Moving the instructions from the physical realm into an electronic memory array created the stored program concept. It made computers adaptable without hardware changes, establishing the baseline for all modern software engineering. We define a modern stored program system precisely. It is a computer that serially fetches machine code from a memory unit, loads it into a processor, and performs arithmetic or logical operations on that data. But that concept is strictly an operational theory. For a computer to actually function, it requires a specific physical layout of wires, buses, and silicon to connect the memory to the processor. In 1945, mathematician John von Neumann proposed the hardware blueprint that would dominate the industry for decades. People often use the term von Neumann architecture interchangeably with the stored program concept. They are completely different things. Von Neumann's design is merely one specific physical execution of that broader theory. How a system physically routes information between its memory and its processor dictates its execution speed, its manufacturing cost, and its exposure to security vulnerabilities. A von Neumann architecture computer is constructed upon four distinct interconnected physical components. The first is the central processing unit, or CPU. This is the main piece of hardware that executes the instructions of a computer program. Inside the CPU sits the control unit. It retrieves instructions from memory, decodes them, and generates the electrical signals that direct the rest of the system's operations. The control unit tracks its place using two crucial registers: the program counter, which holds the address of the next instruction, and the instruction register, which contains the code currently being executed. Below the control unit is the arithmetic and logic unit, or ALU. This component handles the actual math, performing calculations on the binary data. The third component consists of the input and output equipment, which is entirely managed by the control unit to interact with the outside world. The fourth component reveals the defining characteristic of von Neumann's design. Both the program instructions and the operating data are housed together within a single, unified main memory array. Routing all information to one shared memory block makes the physical wiring of the motherboard much simpler. However, it forces the processor into a highly rigid, sequential order of operations. Because they share the exact same physical space, program instructions and data are stored using the identical binary number format. To the hardware, they look the same. This creates a massive software advantage. If programs are just data, then programs can operate on, modify, and translate other programs. This allows us to build compilers and linkers, which translate human-readable code into machine language. It also enables the creation of instruction set architectures, or ISAs. These are standardized rules that allow compiled software to run seamlessly across computers built by entirely different manufacturers. Treating executable code and static data identically made modern software engineering possible. Yet, this shared home concealed a severe physical limitation that hardware engineers would spend the next several decades trying to fix. The CPU and main memory do not sit in isolation. They are connected by a physical pathway. In the von Neumann model, there is only one shared system bus. This single set of wires must handle both the retrieval of instructions and data transfers. This creates an absolute physical limit. An instruction fetch and a data transfer cannot occupy the same wires at the same time. When the CPU finishes an instruction, it must pause. It waits for the result to travel across the bus and be written back into memory. Only after that round trip is complete can the processor reach back across the bus to pull its next instruction. This chart shows the historical gap between processor speeds and memory access times. Over decades, CPU clock speeds skyrocketed along a steep upward curve, while the speed at which memory could serve data stayed relatively flat. Engineers call this the von Neumann bottleneck. As processors became incredibly fast, they spent the vast majority of their operational life idling, starving for data stuck in a single-lane highway. The shared memory model also creates a critical security vulnerability. Without separate physical locations, the processor lacks the ability to structurally distinguish between an executable command and a benign piece of data. The CPU blindly executes whatever binary sequence the program counter points to, trusting the information implicitly. Attackers exploit this design by injecting malicious code into memory spaces meant for data. This is known as a code injection attack. When the processor inevitably reads that space, it unintentionally executes the attacker's instructions. The industry did not fully recognize this as a hardware flaw until the late 1980s. Today, chipmakers like IBM have had to integrate artificial intelligence into processors like the Telum just to monitor for and detect these fraudulent instructions. The von Neumann model traded performance and inherent security for simplified, cheap manufacturing. For high-stakes environments, engineers needed a system that severed that shared connection entirely. The primary alternative to this bottleneck is the Harvard architecture, a different physical implementation of the stored program concept. When placed side by side, the structural difference is clear. The Harvard layout's defining feature is physical isolation. Program instructions and data are housed in separate memory units. Because memory is split, the bus structure splits too. The CPU connects via completely independent pathways. Using separate pathways yields an immediate operational result. The processor can fetch an instruction from one block and read data from another at the exact same time. This isolation also provides hardware flexibility. The separated memory units can have distinct physical characteristics. Engineers might store the program code in read-only memory, or ROM, while keeping the volatile data in standard read-write RAM. Severing the shared connection completely eliminates the single-lane traffic jam, granting the CPU true parallel memory access. Parallel access drastically improves clock cycle efficiency. A clock cycle is the basic unit of time a processor uses to measure and execute an instruction. This diagram shows the resulting execution timelines. A von Neumann machine must take staggered steps, using multiple clock cycles to sequentially fetch, execute, and write back. A Harvard machine overlaps these actions perfectly in a single cycle. Running the exact same software on a Harvard architecture requires significantly fewer total clock cycles from start to finish. Separating the paths also means the buses don't have to match. A system could utilize a 24-bit bus for retrieving instructions, while simultaneously moving data along a wider 32-bit bus. But this efficiency comes with a steep manufacturing cost. Supporting dual independent buses requires a CPU with vastly more physical pins, which severely increases complexity and production costs for motherboard manufacturers. Harvard architectures execute faster and isolate code from data to prevent injection attacks, but their physical complexity makes them significantly more expensive to build. Despite its bottleneck, the von Neumann model remains the undisputed standard for laptops and general-purpose computers because its hardware is highly economical and uncomplicated to mass produce. However, there are specific computing sectors where the cost of the Harvard architecture is absolutely mandatory. We see it primarily in microcontrollers and real-time embedded systems. Digital signal processing systems, or DSPs, rely heavily on this architecture's cycle-perfect timing. These machines process continuous data streams, like analog audio signals and real-time biomedical monitoring. It is also the backbone for high-stakes external applications, including aircraft navigation controls, seismic data analysis, and advanced radar systems. General computing accepts the memory bottleneck as a fair trade for cheap hardware, but when a system analyzes flight variables where a single millisecond delay is a matter of life or death, it requires the isolated precision and unyielding speed of the Harvard architecture.